What if the next big thing in clean energy wasn't some brand new discovery at all, but something that's been forgotten? Today, we're diving into a pretty radical idea, a powerful energy source that some researchers claim has been found and then lost multiple times throughout history, a secret hiding in something as simple as a spark. Okay, let's just start with a kind of wild thought here. What if the solution to our energy crisis isn't waiting for us in some futuristic lab, but it's actually hidden away in a dusty notebook from 150 years ago? I know, it sounds like the plot of a movie, but it's the very real starting point for the story we're exploring today.
So, where does the story even begin? Well, it starts with a name you're definitely going to recognize, Nikola Tesla. But we're not talking about his famous AC motors or those giant lightning-throwing coils. Nope, we're looking at a much smaller, almost forgotten observation that apparently puzzled even a genius like him.
Yeah, we're talking way back. According to researcher George Egeley, nearly 150 years ago, Nikola Tesla was messing around with something called a carbon button lamp when he saw something that just didn't add up. A little hint of what Egeley now calls an excess energy process. So here's the puzzle. Tesla's lamp, which had a silicon carbide cathode, was glowing way, way too bright for the amount of power it was using. He was, and this is a quote, baffled and intrigued. But the physics of his day had absolutely no answer for it. So the observation just became a footnote, just this weird unsolved mystery. All right, so how do we even begin to solve Tesla's little puzzle? Let's fast forward to today, where researchers like George Egeley are proposing a really radical explanation. They think the key isn't just tweaking the old theories, but an entirely new kind of thing, something called the condensed plasmoid. So what in the world is a condensed plasmoid? Well, imagine a tiny, self-contained bubble of pure energy. It's described as a quasi-particle, which is basically a fancy way of saying it's a temporary team-up of millions of electrons, all quantumly tangled up and acting like one single powerful unit. And its whole job? To act as a catalyst and kickstart low-energy nuclear reactions. Okay, so let's break this thing down. First, it's a quasi-particle, not one of the fundamental particles you learn about in high school. It's got a very specific shape, a toroidal vortex, which is kind of like a tiny, stable smoke ring made of pure energy. And here's the crucial part. It's only formed under very specific conditions. We're talking short, intense, rapid spark discharges. This is the thing that's supposed to catalyze a fusion reaction. Okay, I know what you're probably thinking. If these things are real, why aren't they in our physics textbooks? Why haven't we heard of them before? Well, according to this theory, the answer is that our textbooks are, well, missing a pretty big piece of the puzzle. So the core argument here, and it's a big one, is that our standard model of electrodynamics, which is incredibly successful, by the way, has a blind spot. It is brilliant at describing charges moving in a straight line, but Egeley argues it almost completely ignores the effects of rotating charges. And he claims that in this missing piece, a whole new kind of physics is hiding. And this diagram from the source material really helps make it clear. See, on the left, you've got the basics. Charges just moving from point A to point B. That's a standard electric current. But on the right, you have charges moving in a loop, a rotating current. The whole argument is that this rotation generates entirely new effects that just aren't accounted for in the standard model. So let's just put this side by side for a second. Standard electrodynamics, it's all about that linear movement, which creates the electric and magnetic fields we all know about. This new theory adds rotating charges, which are said to create a completely new spin field. You can think of it like this. A normal field can be described with a simple arrow, a vector, pointing in one direction. But this new spin field is way more complex and has properties in multiple directions at once, so you need a more advanced mathematical tool called a tensor to describe it. Okay, so we've got this historical mystery, right? And we've got this wild new theory. But how do you actually turn all that abstract physics into a real working device? Well, this is where the theory gets put into practice, using the very thing that might have created Tesla's super bright light, spark discharges. And the process they propose is actually surprisingly straightforward. Step 1, you create a plasma, and you fire a bunch of rapid, intense sparks into it. These little blasts, these transient discharges, are thought to create the perfect conditions for condensed plasmoids to just pop into existence. Step 3, those plasmoids then catalyze a reaction that produces energy. And then, and here's the real game changer, the output is collected directly as electrical energy. And right here, this is where the theory smacks right into reality. This image gives you a sense of what the experimental setup looks like.
Inside that chamber, they fill it with gas and create a plasma. That's that glowing haze you see. Then they hit it with carefully timed high-voltage sparks to try and generate these plasmoids. And this is where George Egeley has reported something really incredible, that under just the right conditions, this whole process can become self-sustaining for short periods, producing energy all on its own.
And this right here is a huge deal from an engineering standpoint. Think about it. Almost all our power plants today, from coal to nuclear, they're basically just really, really fancy steam engines. You create heat, you boil water, you spin a turbine. It's complicated and not always that efficient. This new method, though, claims to produce electricity directly. No steam, no turbines. Just a device that could, in theory, convert a reaction straight into usable power. So, this all leads us to the big question, the one that really matters. Does it actually work? Let's take a look at the reported results. And it's important to remember, these are claims that are still waiting for widespread, independent verification. So the number that matters most in these kinds of experiments is something called the coefficient of performance, or COP for short. Put simply, it just measures how much energy you get out compared to what you put in. Egeley's team has reported a COP somewhere between 2 and 5. Now, just to be clear, in energy science, any COP over 1 is the holy grail. It means you're getting more energy out than you're putting in.
I really want to be crystal clear about what this number means, because it's a really big claim. A COP of 2 to 5 means for every single unit of electricity you feed into this device to get it started, it supposedly kicks out 2, 3, maybe even 5 units of electricity back. This is the extraordinary claim that makes this research both so incredibly compelling and also so controversial.
And so we're left with this really tantalizing question, aren't we? From a mysterious glow in Tesla's lab all the way to modern claims of net energy gain from a plasma experiment, this whole theory challenges what's in our textbooks. So is it the key to a new era of clean energy, or just another scientific dead end? The answer, if there is one, may have been hiding all along, in the simple, fleeting power of a spark.